So thank you very much for having the opportunity to talk on continuous and intensified bioprocessing. So we have our wonderful fed batch platforms. They run in disposable facilities. Why should we intensify? Well, one of the reasons could be, of course, to get more product out of our disposable facilities. Currently, there's a limitation to the amount of kilograms we can produce with 2,000-liter single-use facilities. The solution to getting more out of these facilities is intensifying. So having our normal fed batch, how can we intensify? There's several options, and one thing we can do, and this is done by a number of companies, is using an N-1 perfusion solution. And in this way, let's say what's under the curve, which is which is representative for productivity, can increase because you start with the maximum cell density at the beginning of the culture, and you're productive already in the beginning of the culture. So this is a technology that is used a lot, even as a platform technology for companies like GSK. Another thing you can do is to increase the amount of cells in the bioreactor. And this can be done, for instance, by concentrated fed batch. What you do is you allow the cells to grow exponentially in the beginning, reaching much higher cell densities. And what you see is that the area beneath the curve, representing productivity, can become much higher that way. And the next thing you can do is some clever scheduling, having several of these bioreactors, having them producing every day and in a staggered way, creating even more productivity from your facility. If you extrapolate it even further, then you end up with continuous perfusion. This is really the way to achieve the highest volumetric productivity in time from your system. But what are people actually doing at this point in time? Continuous perfusion as an upstream technology has been around for decades, but it's strictly being used for complicated and labeled proteins because of the prohibitive costs mostly of media, etc. Recently, we see that in the downstream, continuous multicolumn chromatography is gaining a lot of foot on the ground. And it makes sense because using intensified capture with these multicolumn chromatography systems, you can handle much more kilograms from a single batch. So in this hybrid type of setting, continuous multicolumn chromatography absolutely makes sense. Another place where it makes sense is if you have continuous perfusion, which creates a large volume output, which you can concentrate online basically with your multicolumn chromatography. So these hybrid forms are already being used, and you see a number of companies to the right that apply these technologies. Then you have what some people call the holy grail of biotech, one flow, fully continuous process, where you start with continuous perfusion in the upstream and you have continuous downstream steps all the way through. So here, what we see is that because of the challenges and some of the limitations there still are, for instance, regulatory, but also some technical limitations that people are testing these in their advanced labs, like Merck is really far with it. But we haven't seen it coming into routine production yet. And we're not sure how long this will take, but definitely it will find its way into production. The key question, of course, is when and to what market share. I won't go into that further. What I will show you is a number of practical aspects of the upstream part of continuous biomanufacturing. And I want to compare, let's say, starting with the fed batch bioreactor, what you need in terms to make it an intensified concentrated fed batch or perfusion system. So the first thing you need is a retention system. For instance, an ATF, you can also use TFF, something else. And the other thing you need is a big media hold tank in order to provide sufficient perfusion medium. This basically are the two basic extra additional elements you need to perform concentrated fed batch. Because in concentrated fed batch you keep your cells as well as the product inside of your bioreactor, meaning that the flow that passes the filter is waste. If you want to go into a true perfusion mode, where the product passes the filter, you need to collect the harvest as well. You need to have a cell bleed, because in order to extend the run to an indefinite run length, you need a small positive growth of your culture, and this is often achieved by a cell bleed. To the next level, you need to have your media logistics organized. And if your cell bleed is big, you need perhaps an option to clarify the cell bleed. So, simple, right? What you can see is that, we need several additional elements, and we also have a number of additional parameters that we need to develop and we need to control. So there's additional complexity in perfusion, but it can be managed having the right tools. So what do you need when you want to develop such a process, continuous fed batch or perfusion? So we have an entire platform of technologies that is available for the fed batch. We have the Amber 15, the Amber 250, we have the downscaled models at the bench scale. So this is all available for your regular fed batch. You have your media prep and your scale-up. What do we have available to develop our continuous perfusion and concentrated fed batch processes? And I will show you some examples where the Amber 15 has been employed, which is, I think, really interesting. I will show you some examples where some process development work at benchtop scale has been done, but there's also perfusion options in the RM system, which is interesting for your seed expansion and your high cell density cell banking option. There's virus removal filters that can help you reducing the risk when you use a lot of media, and you can take out the virus from the beginning. That will help you with respect to risks at that point in time. There's N-1 and N-2 perfusion opportunities, and also you can connect, for instance, an ATF to the larger scale systems for fed batch, concentrated fed batch and perfusion applications. Last but not least, BioPAT sensors are needed to control your process. Good, then you have your high cell density, and now you need to get rid of your cells, and there's a very interesting technology that I want to briefly highlight as well. So, going to some practical examples, you don't always need very complicated equipment to get some interesting results. What we did here was use very simple shake flasks. Actually, they were 125 milliliter shake flask with 25 milliliter of liquid medium, and they were baffled. And using these baffles, they create sufficient oxygen transfer to support very high cell densities. So different situations were tested, and what is done to mimic a perfusion situation is to do a daily spin down and refreshment of the supernatant. And different situations were tested. So what you see here is that adding, for instance, glutamine helped a lot to get to a high cell density very quickly. At this point in time, the temperature was dropped because higher productivity was being created. And you can see that with this particular media and several different type of feeds, cell densities up to 50 million cells per milliliter were achieved with 1 volume a day refreshment. It's pretty amazing inside a shaker. What you can also see is that at the end of the run, using some more feed or using glutamine addition, the longevity extended. You can also see the product titer, which is pretty amazing, and it ran up to about 40 PCD in this case. And with the high cell density, you get pretty neat titers in a perfusion setting. pH, not controlled, but pretty constant and in acceptable ranges, except for these ones that dropped. There you also see that the pH drops, so there's a metabolic shift causing this. Nice, but if you really want to do some DOE type of work and you want to have deep process knowledge, yeah, you need the amber. I mean, it's as simple as that. And here you see a very nice example where the amber has been modified, creating a sedimentation situation. And this is work from Glycotope, and they were able to show that cell densities, viabilities were very similar to a 1 liter bioreactor. They did have different titers, but product quality was very indicative. And they were able to use the DOE power of the amber to develop their process in a very much more quick way. Another example, and this uses, this is at the medium scale, at the bioreactor scale, 5 liter actually, where in this case a TFF system was connected. Here you can see that the cells are quickly grown up to 90 million cells per milliliter by an optimized protocol. Viability is high, temperature is dropped, cells continue to grow a little bit. There's no biomass control in this specific case, but the idea of the example was to check different type of filters, because one of the issues that you can encounter is product sieving, and this is a particularly clear case where, in this case, filter A has a substantial product sieving. The titer in the bioreactor is represented by the brownish curve, and you can see that filter B had no product retention whatsoever. So a very clear case. Scaling up, once you have developed such a process, is now easier than ever with the second generation of the SDR bioreactors. And if you want to know more, you can come to the booth. Just to show what you can do, this is a 500 liter example where at 500 liter scale, and this is actually in my previous, one of my previous jobs, we were able to achieve over 200 million cells per milliliter. So that's quite a lot in a concentrated fed batch mode. And what you see is that the titer goes up accordingly. This is another example showing that even at 2000 liter scale you can achieve very high cell densities and get the same performance as in a stainless steel bioreactor. And also, if you want to know more about this example, you can talk to me afterwards. So, downside of working with high cell densities is that you have to remove the cells. And that's where there's a very nice new interesting development, which is the KSAP bioreactor. It's a unique technology where cells are not just spun down, but you have a balance between the gravitational force and the flow, keeping the cells in a fluidized bed. It's very, very mild for the cells and make sure that they don't pop open and release the contents. So, in conclusion, why use intensified and continuous processes? They enable single-use facilities to be used not only for small products, but also for mid to large volume scales. Sartorius, so full continuous holds the promise for superior product quality, but some work still needs to be done. Sartorius has some highly suitable solutions, and we are willing to tell you all about it when you visit the booth. For instance, in the bioreactor arena, I didn't mention anything on the downstream, but there's also some great membrane adsorbers out there, and PAT solutions that can assist in running these processes. Unfortunately, I cannot tell you anything about the great new stuff in the pipeline, but I can assure you that there is some great new stuff in the pipeline. So I would like to thank you for your attention, and I would like to hand over to the next speaker.